A normal distribution is defined by its two parameters, the mean and the standard deviation. Consequently, there are an infinite number of normal distributions. That's because there's no limit to the possible values for the mean or the standard deviation. There is one normal distribution, however, that gets special status. This distribution is called the standard normal distribution. Let's look at what makes the standard normal distribution special. It is a single normal distribution in the infinite universe of possible normal distributions. As with any normal distribution, it must be defined by its two parameters. The mean of a standard normal distribution is 0. The standard deviation of the standard normal distribution is 1. That is all that defines a normal distribution as a standard normal distribution. If the distribution is normal, if the mean is 0, and if the standard deviation is 1, then it is a standard normal distribution. The scores in the standard normal distribution also have a special name. They are called z-scores. Here is a picture of the standard normal distribution. The scores along the horizontal axis are z-scores. As with any model of a distribution, the vertical dimension represents density. Note that the curve is at the highest point when the z-score is 0. A score of 0 is the mean of the standard normal distribution, and normal distributions have their highest density at the mean. That is, we expect more scores around the mean of the distribution than anywhere else along the score range. There is something interesting about z-scores, and this is what sets apart the standard normal distribution as a special distribution. A z-score of 1 is one standard deviation above the mean, because the mean is 0 and the standard deviation is 1. A z-score of 2 is 2 standard deviations above the mean. Similarly, a z-score of -2 is 2 standard deviations below the mean. The standard normal distribution is special because the scores are in standard deviation units. Statisticians will talk about raw scores, which is the name that they use for original scores, and standardized scores, that is, scores that are in standard deviation units. On the standard normal distribution, these are the same. Note in this picture the z-scores of -3 and +3. These are both 3 standard deviations from the mean. So we should expect over 99% of the distribution to be between these two scores. And isn't that what it looks like in the picture? Indeed! If we want to convert scores that are normally distributed so that they will have the distribution of a standard normal distribution of scores, we can do so. All we need to do is convert from the original scores, that is the raw scores, to a z-score. Here are the conversion formulas to convert the raw score to a z-score, or vice versa. To convert to a z-score, we simply find the deviation of the score from the mean, then convert that to standard deviation units by dividing by the standard deviation. Let's try it. This is a little script I wrote to illustrate the conversion of raw scores to z-scores. Suppose a score of 120 is from a normal distribution with a mean of 100 and a standard deviation of 10. Here's a conversion to a z-score. We subtract the mean of 100 from the score of 120. That's going to give us a deviation score of 20. Then we divide by the standard deviation of 10. The result, of course, is a score of 2. We say that the z-score corresponding to a score of 120 is 2. That's because 120 is 2 standard deviations above the mean of 100. Suppose a score of 45 is from a normal distribution with a mean of 50 and a standard deviation of 5. The deviation score is 45 minus 50, or negative 5, and when we divide this by the standard deviation of 5, we obtain a z-score of negative 1. Let's try one that is not quite as easy to calculate in our heads, so that we truly need to use R as a calculator. Suppose a score of 39 is from a normal distribution with a mean of 50 and a standard deviation of 5. We use the conversion formula and subtract the mean of 50 from 39, then divide this result by 5. This gives us a z-score of negative 2.2. In other words, a score of 39 is 2.2 standard deviations below the mean if the mean is 50 and the standard deviation is 5. We also have a formula for converting a z-score to a raw score. We multiply the z-score by the standard deviation and add this to the mean. Let's try it. Suppose we want to find out what score is 2 standard deviations above the mean on a normal distribution with a mean of 100 and a standard deviation of 10. To find out, we multiply 2 by the standard deviation of 10, add it to the mean of 100, and that gives us a score of 120. (120) is 2 standard deviations above the mean of 100 when the standard deviation is 10. That's pretty obvious, right? Let's try one that's not so obvious. Suppose we want to find out what score is 1.5 or 1.5 standard deviations below the mean on a normal distribution with a mean of 30 and a standard deviation of 2.5. We multiply the standard deviation of 2.5 times negative 1.5 and add the result to the score of 30. Note that this is a subtraction because we're adding a negative number. We find that 26.25 is 1 1/2 standard deviations below the mean. You can find percentiles and percentile ranks of the standard normal distribution in tables in statistics books. There's a historical reason for this. In the days before we had statistical software like R, to find out a percentile or percentile rank on a normal distribution, statisticians or students would convert to a z-score and then look this up in a table. We don't have to do that anymore. We have software that can handle any normal distribution and provide the percentile or percentile rank without needing to convert to z-scores or look anything up in a table. Consequently, the standard normal distribution has less importance than it used to. Now you'll still hear it mentioned, and people will still refer to standardized scores as z-scores, so it's important to know what they're talking about. Your next mission, should you choose to accept it, will be to learn how to use R to calculate percentiles and percentile ranks on a normal distribution without converting to z-scores. If you're willing to watch more videos, I'll show you how to do this.